Hello everyone, my name's Sam Howiton and I'm your lecturer for this course on integral transforms, which is one of the short options. First, I'd like to congratulate you on choosing this course because I think it's one of the nicest pieces of mathematics that you get to do this year, second only to complex analysis in the range of topics you cover, the beauty of the mathematics and the huge number of applications that you will see you can do from it. So this is going to be 9 lectures in this course, and we'll start this first one with a little bit of housekeeping. So, well, we can all read this. There's lecture notes, which were written by Richard Earle and then edited by me, so they're quite comprehensive and they cover the syllabus for the course very closely. There are going to be 9 lectures, as I said, and they will follow the lecture notes pretty closely. But obviously they're going to be shorter, and where I can, I've chosen to have different examples so that you see different ways of doing things. Just a note on the lecture notes and the numbering, numbers of theorems, examples, etc. follow the lecture notes, but if you see something called example 12a, for say, in the lectures, then that is related to example 12, but it's a different version of it, so I hope you'll get something new from looking at these lectures. I do obviously urge you to read the lecture notes as well as these slides. Panopto, the system we're using to record these, is a pretty inaccurate captioner. It does produce audio captions, but they're pretty terrible. All right, Panopto, it's not your fault. They are terrible captions, but you can usually make out what they mean when you look at the slides. So if there's something absolutely impossible, just let me know. There are going to be 2 problem sheets. The first one will cover, roughly speaking, lectures 1 to 6, although in fact, if you get to the end of lecture 6, you've overshot what you need for that problem sheet. And then the second one will cover lectures 7 to 9, but some of lectures 4, 5, and 6. So I suggest 2 tutorials or classes or whatever your college is going to do, and split them as written down here. Finally, going up a bullet, in the lecture notes there's a short preamble about integration, which is not a formal part of this course, but I do suggest that you read this. It's important background so that you understand what I mean in the course when I say that a function is integrable. Now, we're going to take a fairly applied point of view in the course. We're not going to rigorously prove absolutely everything we do. We are going to use mathematical intuition and maybe a little bit of physical intuition here and there. But I do assure you right from the word go that every single thing we say in this course can be proved rigorously, and indeed there are courses you can take which will let you see that in more detail. So this is a little bit of a view from 10,000 meters, but it's I want to give you a flavor of what the rigorous treatment looks like without drowning ourselves in epsilons and deltas and so on. So we're going to do 3 things in the course, roughly speaking 3 of these lectures each. The first one is the theory of distributions, and actually this is in some ways the most novel material for you. It's also probably the most recent because this theory was only really fully developed in the second half of the 20th century. So it's quite an unusual example for you of relatively recent mathematics in your second year. And this is what used to be called generalized functions. If you think of it as how can we make a proper mathematical interpretation of something like a point charge or a point mass or a point heat source, or how can we join up continuous and discrete probability in the same framework, or how can we differentiate a step function? All of those things we're going to see how to do. And it's a wonderfully simple and powerful theory which lets us make sense of an awful lot of things which otherwise would be really quite hard work. Then we're going to move on to discuss two kinds of integral transforms, and these are ways of representing functions which look like the Fourier series that you've already seen, but instead of using a countable set, a discrete set of basis functions like the trigonometric functions, they use an uncountable set, a continuous set of basis functions. In this case, there will be exponentials, either real exponentials or complex exponentials. And along the way, we're going to see applications of all of these things to a huge range of problems, many of them to do with differential equations, because these tools are particularly well developed for differential equations. But as you go on in your mathematical careers, you will see these ideas cropping up everywhere, from really very abstract group theory right the way through to data science, fluid mechanics, solid mechanics, all sorts of things. So this really is a very central course. We're going to start with some motivation. We're going to start with motivation for the famous delta function. And the delta function is, if you like, the canonical idea of distribution. If you get your head around the delta function, then you've got your head around the whole thing. And we're going to start with a very simple example from probability. A lot of our examples are from probability. And this is quite a thought-provoking one, actually. Suppose you have a random variable, x, which has the normal distribution with mean 0 and variance sigma squared. Okay, we know all about that. It has a typical bell-shaped distribution like that. And the density there, I've written it as f sub x to tell us it's a random variable x, and the superscript sigma to remind us that the standard deviation is sigma, is 1 over the square root of 2 pi times the variance times e to the minus x squared over sigma squared. And the important features of this are that when you graph this distribution, famous bell curve, the width of it is of order sigma. That is to say, if you go a couple of standard deviations, 1.96 standard deviations either side of a mean, you capture 95% of a probability. So the probability is all concentrated within a few standard deviations of a mean, and then the height of it is order 1 over sigma, and because the area is 1 over sigma times sigma is 1, that tells you that we would expect the area to be of order 1, and of course, because it's a PDF, the area is exactly 1, whatever the value of sigma. That's just built in, isn't it? But what happens when you let sigma tend to 0? You may never have thought about that, but what happens as you let this get narrower and narrower, and this get higher and higher? What happens? Well, if you take any value of x which is not 0, then as sigma tends to 0, the probability density function tends to 0. So if we go back and have a look at it, we have a 1 over sigma squared here, which is going to go to infinity as sigma goes to 0. But then we have e to the minus x squared over 2 sigma squared. For any x not equal to 0, e to the minus something over sigma squared goes to 0 far, far faster than 1 over sigma goes to infinity. So the limit for x non-zero is 0, but now you put x equal to 0, and this thing is 1 all the time, whatever sigma is, and so the limit is infinity. So the limit function isn't a function at all, because it's 0 everywhere else, that's okay, but it's infinity at the origin. But now look at the limit of the integral. The integral of f dx is 1 for all sigma, and therefore the limit as sigma goes to 0 of that integral is 1. So that limit has preserved the fact that this is a probability distribution. It's preserved the fact that the area under the curve is always 1, even though the function appears to have gone to 0 everywhere. In fact, it has gone to 0 everywhere for x not equal to 0. So this just gives us the idea that there's a function in quotes, because it isn't an ordinary function, but we're going to call it delta of x, the delta function, Dirac delta function, named after the famous British physicist Paul Dirac, which has the property that it is 0 everywhere except for when x is 0, but its integral is still 1. Whatever this may mean, and we're going to see what this means as we go on. And if we think about the probability interpretation, well, what's the PDF of a random variable which has 0 standard deviation? It's not random at all, is it? It's equal to 0 with probability 1, and so all of its probability mass is concentrated in the single point x equals 0. Now let's have a look at the cumulative function, the density function. So we'll call this capital Fx, which is the integral from -infinity to x of f, the density fx sigma of s ds, and it's the probability that x is less than or equal to x. Notice there's a less than or equal to there. And so, of course, as we know, by the fundamental theorem of calculus, when sigma is positive at least, everything is smooth, and you can differentiate this to get d capital F equals little f. And of course, when you draw the graph of this thing, you have the usual sigmoid curve like that. And now we say, well, what happened to this when sigma goes to 0? Well, what's the limit? The limit is 0 when x is negative and 1 when x is positive, because if you have a random variable which is always equal to 0 with probability 1, then the probability of it being less than 0 is 0, and the probability of it being greater than 0 is 1, and this function is continuous from the right because of the way that we define the cumulative density function. So what that tells us is that if the derivative of the cumulative density is equal to the probability density when sigma is positive, maybe that's true for the limit as well, in some sense. Maybe we have that the derivative of this step function h, which goes from 0 up to 1 with a jump at the origin, a jump of 1, maybe the derivative of that is equal to this thing we've called delta. And if that's true, if we can make sense of that, proper mathematical sense of that, then what we've done is we've worked out how to differentiate properly a function with a jump in it, a step function, not just away from the step, but including the step as well. And of course, that's really good, because what it does is it tells us something about how big that jump is. Knowing the derivative away from the jump doesn't tell you anything about how big the jump is, but if you know something about the derivative at the jump, that should tell you how big the jump is as well. All of this, of course, remains to be made mathematically sensible, but this is the intuition of it. So here's another example. We've all done simple mechanics and the thing called an impulse. So the idea here is you're going to have a particle which has position x of t, and it's sitting there at rest with x of t is 0 for all t less than or equal to 0. And then we apply a force F of t when t is positive. So Newton, of course, tells us that m d2x by dt squared, call it mx double dot, Newton type notation, and that is equal to F of t. Very simple. Now let's suppose that this F of t is only positive when t is between 0 and some short time tau, and then it's 0 afterwards. And let's call the integral from 0 to tau f of t I, and let's suppose that's a constant. So if you integrate once, you can integrate this equation once, nice linear equation, the integral from 0 to tau of mx double dot. That's the change in mx dot from 0 to tau is mx dot of tau, because x dot of 0 is 0. You notice we put in a less than or equal to here, so that x is 0 and x dot is 0 when t equals 0. And so that's mx dot of tau, and that is equal to the impulse, or this quantity we've called I. And then what you do is you let tau tend to 0 with I fixed. For example, you might take the force to be a constant over tau over the interval, a kind of top hat function. Your force would be 0, go up to a constant, and then come down again. And this is what you call an impulse, and the velocity is then 0 and I over m when x is less than or equal to 0, and when x is greater than 0, in the limit that tau goes to 0. So, again, if we use the idea of differentiating a step function, because this is a step function, it goes from 0 to I over m, what we ought to have is that the equation of motion of this function in the limit that tau goes to 0, so all the force is concentrated at time 0, it should be m times the acceleration mx double dot is equal to I times delta of t. Again, can we make this more rigorous? There's a footnote here that says I've been quite careful with my less than or equal to's and my greater than at time t equals 0. This is beginning to look a bit fiddly, and in fact, as we shall see in a few lectures, in a couple of lectures, it's irrelevant. The theory we're going to develop doesn't care what the value of the function is at x equals 0. It can be, you can take the left limit or the right limit, and it really doesn't matter. So not to worry about that. Third example, a point force on a string. This is a very basic prelims or even A-level mechanics problem. You have a thin wire with a tension T in it, strung between two supports, and then you hang a weight from it in the middle, and you ask what's the displacement. Well, it's a thin and light wire, so the only force involved are the tension here and here and the weight here. There's no weight for the wire itself, and it's a simple matter then to say that to find the displacement you simply join up straight bits of wire here with a force balance at the weight, which says that the component of the tension in the vertical direction is equal to the weight. So, writing that down as differential equations, you have d2y by dx squared is 0 away from the weight, and at x equals 0, which is where the weight is, the wire is continuous, so there's no jump in the wire. This square bracket notation means a jump. And then here's your force balance. The weight is equal to the tension. Now this should be the sine of the angle, but because the displacements are small, the sine of the angle is the same as the tangent of the angle, approximately, and so the tangent of the angle is dy by dx. So that's why we have dy by dx there. And it's a simple matter, of course, to solve this. You can just write down y is a linear function for x between minus L and 0, and another linear function between 0 and L. Save yourself some work by incorporating the boundary condition that y is 0 at x equals minus L by writing your linear function as some constant times L plus x or some constant times L minus x. And then you're automatically continuous at the origin as well. You now then have to simply work out the force balance, and that tells you what the constant, the W over 2t, is. And then, well, I want you to go away and think about this. Can you convince yourself that t d2y by dx squared is equal to, now this is a mistake in the slides, it should say W delta of x. So there's a missing delta of x there, apologies for that. And put together the hints that we had before. What are the first and second derivatives of a piecewise linear function? Well, the first derivative is a step function, the second is a delta function. Go away and just work out the details. Quite an interesting little calculation. So let's take a step towards defining this delta function. Suppose there is a thing called delta of x, and suppose delta is 0 when x is non-zero and its integral is 1, whatever this means. So let's not get too picky about this. We'll just say, suppose there is a thing where this is going to be, well, we're going to interpret this quite liberally. Suppose we take a continuous function, we'll call it phi, and then what we're going to do is we're going to multiply delta of x by phi of x and then integrate. So we're going to take an integral like this and we're going to put a phi of x in here, and then we're going to work out what's this. Well, if delta of x is 0 for x not equal to 0, then we don't need to bother about the integral from minus infinity to a minus delta close to the origin, capital delta, a minus capital delta close to the origin, or the integral from plus capital delta to infinity, because we have the delta of x bit vanishes. We don't care what phi does there. So then we're going to do a typical little analysis trick. We add and subtract something, in this case phi of 0. So we write this phi of x as phi of x minus phi of 0, and then we add phi of 0 back in again. And then we split it up into 2. Delta of x times phi of x minus phi of 0 integrated, and then this is a constant, so it can come out of the integral phi of 0 times the integral from minus delta to delta of x, little delta of x dx. Okay, so we'll leave the first part alone. What's this going to be? Well, if this statement is to make any sense, along with this one, the integral from minus infinity of delta should be the same as the integral from minus capital delta to plus capital delta of the same thing. So this integral here, integral in inverted commas of course, that should simply be 1. And so this term is phi of 0. Now we think about this one. Well, what happened to this one? Well, phi of x minus phi of 0 tends to 0 as capital delta tends to 0, and that's because this function phi is continuous. So if there's any justice, this term here should vanish in the limit. And if you want to make that sound a little more rigorous, you'll say for any epsilon greater than 0 and for all small enough delta, the modulus of phi of x minus phi of 0 is less than epsilon. This is just the definition of continuity, standard continuity. A small input x between minus delta and delta generates a small output change in the output. And so what you hope is that you can make this integral as small as you want. Of course, you can't make this a rigorous argument as it stands, but you would like this to be true. It's natural to assume that if this bit is going to 0, as this capital delta tends to 0, then the whole lot should go to 0 as well. So what you conclude is that the integral from minus infinity to infinity of delta of x phi of x dx should be phi of 0. And this, unlikely though it may look, is actually the key to making a rigorous definition of this thing that we've called delta of x. And what we do is we essentially abstract from this notion of multiplying by a function and integrating. What we do is we pull out from that the essential features of it that don't depend on the nitty-gritty of doing an integral. We say, very mathematical thing to do, what properties of an integral when this is an ordinary function, not this thing we call delta, what properties might we be able to preserve even when we have this idea of a delta? And by doing that, we're able to give a rigorous definition of this delta, and that is what we're going to do in the next 2 lectures. So that's the end of immotivation. In the next lecture, we're going to have a little look at some groundwork, which will let us set the whole theory up in lecture 3. So that's all for now. I will see you next time.